So hi everyone. So we are Team Obsidian. So that's Edmund and me, then Dev. So we placed second in the MineRL BASALT competition. The interesting thing is our approach doesn't use any sort of human feedback, and we are using a very, I would say, domain agnostic method, and still are able to get near the top performance in this task. So our method is called inverse Q learning. This is actually a very recent work that was presented in this NeurIPS conference as a spotlight. And this is essentially a new state-of-art method to do imitation on a bunch of environments. And so I can just go into the details on how it works first, and then we can go into the more MineRL specific implementation. So next slide. All right. So how inverse Q learning or IQ-learn works is it's a novel framework that represents, that essentially learns a single Q value to do imitation learning. And the benefit of this is by having a single Q value, you can represent both the policy as well as the reward. And this gives you a lot of advantages compared to prior methods. So they are first, it's dynamic aware, it's non-adversarial, you can get robust convergence guarantees. It has very simple optimization, it can work both offline and online. For our BASALT approach, we essentially use an online version of IQ-Learn that is with access to the simulator and a recurrent listing policy. And we found that is very good in itself without too many modifications. So next slide. Okay, I will sort of motivate this approach first. And first I will go to more how inverse RL works. So I'm assuming some people have some knowledge of what an inverse RL tries to do, but I will just go into that further. So the goal of inverse reinforcement learning is to figure out a reward function from expert data such that the behavior learned from the reward matches the expert. And this can be implemented using some sort of GAN-like setup where you have a generator that's based on a RL sample generation process. So it's some sort of policy network, and you have a discriminator that looks at the policy samples and the actual expert samples and says whether it's true or false. And it acts as a reward to train your RL agent. And there are two popular works in this area. That's Gale and Aero, which do this. The problem with this methods are usually they're hard to stabilize, they're difficult to converge, they don't scale well, they're too many moving parts because essentially you're training a GAN using RL, which is not a good combination at all. So next slide. Right. So the benefit our method presents here is you can totally avoid this optimization in a loop scenario where you are learning a policy, use that to learn a better reward, use that to learn a better policy, and so on. But so instead of recovering reward functions from the expert, if you try to recover Q values directly, you have the benefit that you get a single non-adversarial optimization. And then you can just simply optimize this Q function and recover the policy and the reward afterwards. And so this can scale well to very complex environments. It has good convergence guarantees. It's very stable. And I won't go into too many details of the results, but if you're interested, you can also check out the paper. Okay. So how can we get the policy and the reward from the Q function? So this is actually very easy. So if you know the Q function, you can write the policy as a Boltzmann distribution. So it's some sort of e power Q by Z energy model, or in case of normal Q learning, you can write it as a argmax of the Q function. So if you know the Q function, it's very easy to know the policy. Similarly, you can get the rewards if you know the Q function by using the Bellman equation. So if you look at the Bellman equation in the bottom, if you just move the second term on the right to the left, you essentially get an expression that writes a reward in terms of the Q function of the current state and the Q function of the next state. And that is sufficient to also express the reward. Okay, so next slide. So this actually gives a very simple algorithm where you take a bunch of expert data, you take a bunch of online interactions with the environment, you train and you use this to train a Q network with some sort of modified critic update rule. And once you have the Q network, you get the policy and the reward. This can actually be implemented in less than 15 lines of code on top of existing SAC or soft skill learning methods by just modifying the critic update. Yeah, and we also have some theory part, so I will just go into that a bit slightly. But you can essentially theoretically show that doing inverse reinforcement learning is equivalent to doing inverse Q learning. That is, if you're learning reward functions, that is same as learning Q functions, and you don't lose the benefits. The advantage over here is you can actually just do a simpler optimization. So that's how it works and adjust. Okay, next slide. So I think I will just pass to Edmund to talk about how we implemented IQ-Learn on MineRL.
Great, thank you. Yeah, so I'm going to go through some of our implementation details. To start with, the observation space we used was composed of the visual image along with the item information. And we used a stack of the n most recent observation frames, and this varied a bit depending on the task. And then for the item information, we just used a vector representing the inventory and the equipped item. Then for our data preprocessing and augmentation, we removed all the no-op actions from the data set as we figured they weren't relevant to the tasks. We applied a random frame shift as data augmentation along with a small amount of Gaussian inventory noise. And then we also used data regularized Q in our objective function, where we basically averaged the Q function and the target Q across the augmented and non-augmented state samples. So for our action space, we used a discrete action space. I think it was very similar to the one from the baseline. So just 12 kind of basic actions along with all the equip actions. And one thing we did here as action shaping is that we implemented a confidence threshold on the throw snowball action. And without that, we were seeing that we were getting, the agent would terminate the episode early on actions where it was giving that action a low probability. Great. So for our model, we used a CNN, an LSTM, and a few linear layers. So yeah, we passed our image data through the CNN, and for the CNN, we used the first n layers of a pre-trained mobile net, and the number of layers varied depending on the task. Then we combined that with the item information, passed that through the LSTM and the linear layers to get the Q values for each action in that state. And yeah, using the LSTM was really important for our results. It allowed the agent to navigate better. For example, I think before we used the LSTM, I don't think we ever saw the agent swimming. And afterwards, it seemed sometimes to be able to swim. Yeah. Oh, and I'll also note, so we were doing the online version of IQ-Learn. So we were sampling from the expert data and the agent's interactions with the environment. So here's a summary of some of our key hyperparameters. We allocated the time per task, like so, with less dedicated to the cave task and more to the house task. And then the main parameters we searched over were the sequence length we used to train the LSTM, along with the number of CNN layers. There was a kind of trade-off between those two in terms of the what the GPU had the RAM to be able to accommodate. And in particular, we found that on the waterfall task, using a longer sequence length was really helpful, even though we had to use a much simpler model. This allowed the agent to, some of the time at least, place a waterfall and then remember that it had placed a waterfall, try to take a picture of it rather than just kind of run off and continue exploring. Yeah, I think that's all I'll say here. So with that, we just show some of our results on the find key. So these graphs are looking at the eval episodes used in the competition evaluation and kind of classifying them into some categories. For our find cave agent, I think this was our worst agent. It, could explore, climb hills, but would often get stuck. Our waterfall agent was, I think, our most successful. It was able some of the time to kind of meet the bare requirements of the task of placing a waterfall and then taking a picture of it. Yeah, and definitely I'm cherry picking to show the best clips here, but hopefully these graphs representing the range of outcomes is more descriptive. For the animal pen task, most of the time our agent would just kind of build a lot of fence. Here I'm showing a time when it found some pigs to build near. Yep. So yeah, it was exciting to see these kind of like moments of success, and that. And then on the
so Rohit, do you have a question?
Yeah, on the previous slide, the numbers on the graph seem to add up to more than 100%, which makes me think I'm not interpreting these numbers correctly.
Let's see. That may be an error on my part. They should add up to 100%.
Okay.
Yes, that's an error on my part.
Okay, cool.
Yeah, and then on the building the house task, the majority of the time our agent would just build a kind of jumble. Here's a clip of it doing that. And using the LSTM did seem to help it make a jumble of stuff that was more confined to one location rather than just kind of spreading building materials across the map. Yeah, so as you can see from these results, there's definitely more work to do on this on these tasks. And with that, I'd like to thank the competition organizers. I'm very grateful for the opportunity to participate and learned a lot. So thank you very much. And Div, do you want to say anything to?
I'm sure. So yeah, thanks a lot for the organizing competition. I would say, like, for us, this was very exciting because we were able to take a very simple model-free approach and able to make it work without any human feedback, any sort of like domain knowledge. And we didn't actually think like our agent would be that good. So we were, I would say, somewhat surprised that we were on the leader, that we came very like second place on the competition. And all our code is open source. I also released like the code base for the IQ learning work. So feel free to adapt it for future approaches. If you have any questions on how this works, how this can be used, and let me know. It'll be exciting to like further this and just like using human feedback, other stuff. So I think that'll be very exciting.
Cool. Thank you so much, both of you. Yeah. Any questions? Oh, actually, Vinicius has a question. Go ahead, Vinicius.
Hi. First of all, congrats for the work. That's a very interesting algorithm. I like the simplicity, so that's what's really interesting. I have two questions actually. So the first one, so how did you allocate the hours for each task? So I assume it's like was there any measure of conversions for your queue network, or was more or less based on the task complexity?
So I think I guess like our measure was basically the loss. So when our loss stopped converging, and I think it depended on the task. So I think for the build house, it took a lot of time. So I think we were training our models over for more than 3 days, depending on the sequence length of our LSTM networks. And I think for find cave and I think waterfall, I think it was like around like half a day or 1 day of training. So I think those were smaller, but I think we were basically measuring when our losses stop converging.
I see. I have another quick question, if I can.
Yeah, go for it.
So I saw you use a mobile net to extract some features for the from the image. That was something we also thought about that. Can you just talk a little bit about your experience, if you think it was worth it or not? Just stuff related to that.
Yeah, I think Edmund, do you want to take this?
Yeah. Let's see. So yeah, we used the pre-trained mobile net, but we did leave it free to. We did update it during training. So yeah, it's hard to say. We didn't really do a kind of full ablation on this, so hard to say whether this particular CNN architecture was helpful.
We were talking about that, like our team, like, oh, is it gonna work? Because it was trained with real image. How about Minecraft? But maybe can still extract some relevant features. So we were not sure. I think in the end we ended up dropping and just trained the CNN from scratch. But I was just curious if it was a good call or not.
Yeah, I will say like I feel like it's somewhat useful in like terms of recognizing like better than just working with raw pixels. So it probably might know something about like what a tree looks like, what a maybe an animal or human looks like, even if it's like very pixelated. Maybe you can also train this networks using some sort of like contrastive pre-training methods, and that way you can like it might know more about how to work with Minecraft like environments. So you could use methods like Moco or something, and I think that might actually be a good way to pre-train these networks.
Thank you very much.
Yeah, Tom.
Yeah, thanks. Yeah, thanks for the great presentation. Just a quick implementation question. Maybe I missed that, but you mentioned that you would do some, basically the online version of the algorithm. How was your split between training on the demonstration data versus on the online version?
Right. So I think in our case, we just did a 50-50. So we have like some sort of replay buffer, and we had like a sort of like an expert buffer, and we were just like loading a batch for like an expert batch and a policy batch each iteration, and just essentially taking 50-50 and training on that.
Mm-hmm.
I think we found like that worked pretty well. I think if you have like very sparse data, maybe it might make sense to just have like a bigger policy contribution. But I think for our experiments, we found like that was good enough.
Did you like already start with that, or did you do some like pre-training on just the demonstrations?
No, we just directly started with the online. So we didn't do any offline pre-training kind of thing. Yeah.
Thanks.
Yeah.